Hey, sports fans! This is a video in an attempt to help you understand how to why we switch variables and to kind of give you a visualization of how that works in integrating and finding the area between curves. So we have this problem from our notes from yesterday or the day before, whenever it was, and the problem was find the area of this shaded region in red. All right, so that was the problem we were charged with, and we said, hey, this is a great problem, but if we want to do it properly, we're going in terms of x, right? Integrating with respect to x, we're going to have to divide this thing into kind of the blue part, find that area, and then we'll have to find the area of the yellow part and add them together. Right? That was, we said, hey, if you want to do it with respect to x, you've got to break it into pieces. And you guys said, why, Mr. Cresswell? Well, if we just, suppose we just took the integral over here in this next picture, we took the integral of the function subtracted like we would. We said, hey, the square root function is above the x minus 2 function, and I want to know basically the area between the curves. If I just did that, I'd take root 2 minus x minus 2, but if I did that, that integral would give me everything from, well, excuse me, from 0 to 4, right? If I did that, that integral would give me this entire area right here, which is not what I want, right? I just want the yellow and the blue from over in this diagram. I don't want that piece down here that we'll color in red here, so we're really confused. But I don't want that piece. So we had to break it up. That was the initial problem. We said, hey, if we did this with respect to x, or with respect to y, this becomes a much simpler integral. All right, so imagine if we took this second diagram up here and we rotated the graph, the picture. In fact, let's get rid of this so we can imagine rotating it. That would give us this picture down here. Okay, and let me just highlight for you again so we're all on the same page and it's all the same color, so we'll make the area that we want red. The area that we want red, or the red area in the new picture, the third picture here, is right here. Right? Well, this becomes a much simpler integral. All right? So once again, suppose, hey, this is actually the y-axis, this is actually the x-axis. Okay, because what we did is we took our picture and rotated it. This becomes an integral of, in terms of y, I take this leftmost function in yellow, which you can't see, this leftmost function here, which becomes x equals y squared, all right, and the rightmost function, which is this one here, and if I just integrate from, this actually happens to be -2 to 0, then I'll just say, okay, -2 to 0 of the rightmost function, which was, let's see, if we put that in terms of y, wouldn't that be -x plus 2, I think? So -x plus 2 minus, oh, sorry, -y plus 2 minus y squared dy. Okay, and that just becomes a simple integral that we know how to evaluate. Now I know what you're saying. You're going, hey, but Mr. Cresswell, in this example up here, we said you told us in the notes that we would go from 0 up to +2 as our limits. And I think that this is actually going to be the same as flipping the limits and taking the negative of the entire function, and you'll get to the same place. For visualization purposes, it helps if we just think about rotating figure 2 right up here, rotating figure 2 around the origin. What we technically should do is the picture that I'll show you in figure 5, I guess you'd say. But so what, just to kind of bring everything together here, what we've done is we've taken, if we look at figure 4, we've taken this picture right here in green and we've rotated it and turned it into this picture in pink right here. Okay, and when we did it with respect to y, it became a much simpler integral. Right, so that's why we did it in that one. Now, some of you are going to be a little bit picky here and say, Mr. Cresswell, the -2 thing is throwing me off. Well, what we really probably should have done it's just not as kind of handy for visualization as we should have kind of, instead of rotated it, we should have reflected it about the line y equals x. Okay, so if you notice, here in this picture, that same area highlighted in pink would be from 0 to 2. Alright, so 0 to positive 2. And if we look at the kind of the comparison between the original figure here in pink and the new figure here in red, you notice that they're just a reflection about the line y equals x. Okay, so either way, like I said, if we took the negative of the integral in figure 3 and changed the limits, that'd give us the same area as this area here in pink in figure number 5. This is figure 5. Okay, so hopefully that gives you a little bit of an idea of kind of what's happening when we change the limits of integration and why it's helpful.